Okay, hello, this is, I don't know, it's a Khan Academy style video, I guess. This is RiceAcademy. I'm pretty sure only Robin will be watching this, so hi Robin. So today we're doing, if my pen will work, there we go, Chapter 8, and we're doing Rotational Kinematics. Kinematics. So I guess we'll start with practice problems. The first one we had was number 4. Okay, a rotating object has an angular acceleration of alpha equals 0 radians per second squared. So alpha equals 0 radians per second squared. Which one or more of the following three statements is consistent with a 0 angular acceleration? So we know that acceleration is just the slope of velocity, so let's draw a graph. So if it's a 0, then we know that velocity is going to have 0 slope, so it's going to be a line like that. But this line could be anywhere and have 0 slope. It could be at 0, it could be a negative value, it could be a positive value. So option A says angular velocity is 0 radians per second at all times. That could work. B, the angular velocity is 10 radians per second at all times. That could also be true. C, the angular displacement theta has the same value at all times. So theta, the displacement, is going to be the integration of our velocity. And that could also be true. So I think it's all three, A, B, and C. So you should get A for this question. So moving on, let me get this out of the way. To our next problem, which is number 6. So the next problem, number 6. A rotating wheel has a constant angular acceleration, just equals some k value. It has an angular velocity of 5 radians per second when t equals 0, and 3 seconds later, so at t equals 3, it equals 9 radians per second. What's the angular displacement? So we're looking for theta of the wheel during the 3-second interval. Okay, so we know that the slope of the velocity, which is w, or not really w, but we're going to call it that, is some constant value. And right here at t equals 0, w, the velocity, equals 5. So, I don't know, this is 5. And then 3 seconds later, wow, this is not to scale, it equals 9. So we have this nice little trapezoid here, so we can just take the volume of it, or not the volume, the area. It's just an integration, really, and we'll be able to find the displacement, since integration of w equals theta, since the derivative of theta equals velocity. Yeah, I'm not making any sense right now, probably. So 1/2 times base, which is 3, so it's 9, equals 21. Okay. So 21 radians. And that is answer B. So for number 6, we get B as our final answer. Next problem is number 3 of the real problems. Okay, the Earth spins on its axis once a day, so we can already figure out theta. It has a complete revolution. We don't know the radius yet. Don't know the time. Never mind. Okay, I'm being silly. So it spins on its axis once a day and orbits the sun once a year. And 1 year equals 365.25 days. Determine the average angular velocity, so it's that, in radians per second of the Earth as it A spins on its axis and B orbits the sun. So we know that the angular velocity, this thingy, equals delta theta over delta time. And for spinning on its axis, we know that delta theta is going to be 2 pi. Every time it spins, it's completed a full revolution. So delta theta is going to be 2 pi. Delta time is 24 hours, but we're going to change that to seconds because I like that better. So 24 hours times 60 minutes times 60 seconds. And all of that will give you, I believe, 86,400 seconds. So now we take this 86,400 seconds and we divide 2 pi because we're looking at delta theta over delta time. So 2 pi over 86,400 equals, so this up here is in radians, this up here is in seconds. So our result right here is going to be in radians per seconds, which is what we want. So if we take that, we're going to get 7.27 times 10 to the negative fifth. Oops, that is not 10. 10 to the negative fifth. And that is in radians per second. So that's our answer to part A, the angular velocity of a daily revolution. Now we want to find part B. So part B, our delta theta is still going to be 2 pi because we're talking about 1 full revolution, but instead of the Earth revolving around itself, we're going to be talking about the Earth revolving around the sun. So that's a different time period. 1 year is equal to, let's see, it said 365.25 days times 24 hours per day times 60 seconds, or 60 minutes times 60 seconds. And if we multiply all of that together, we're going to get, 31,557,600 seconds. That's a big number. Okay, so then we just divide 2 pi by 31,557,600, and we get, 1.99 times 10 to the negative 7 radians per second. And that is your answer to part B. Yay. Alrighty, next up is number 9. A Ferris wheel rotates at an angular velocity, so this isn't W, I think it's omega. We're going to call it omega. It rotates at an angular velocity of 0.24 radians per second. Starting from rest, so I guess omega initial is 0 radians per second. It reaches an operating speed with an average angular acceleration, fish, alpha, yes, of 0.03 radians per second squared. How long does it take the wheel to come up to operating speed? This one, so nice. So we know that the final angular velocity is 0.24 radians per second. So final equals, what does this look like? It looks like we're going to use that beautiful little formula, VF equals VI plus AT. So translating this over, it's just this. So plugging that in, okay, our final velocity is 0.24 radians per second. Our initial is 0 plus alpha time. So 0.03 times time. And then t equals 0.24 over 0.03. And that comes out to t equals 8 seconds. Beautiful. Alright, number 13. Two people start at the same place and walk around a circular lake in opposite directions. One walks with an angular speed, omega equals 1.7 times 10 to the negative 3 radians per second. So that's the first person. Second person with an angular speed of 3.4 times 10 to the negative 3 radians per second. How long will it be before they meet? So we know that omega equals delta theta over delta time. That's not time. Delta time. So what we want to find is their displacement. In order to do that, we just need to take, so delta theta equals their angular velocity times delta time. So we just have to set it up like this. We know that when they meet, their total displacement for the both of them will be one full revolution. It'll be one full revolution because they're starting at the same place. So we can say, see, let's write it up here. 1 times t plus omega 2 times t equals full revolution, 2 pi. So plug that in. I guess I should put that in parentheses. Plus 3 times 10 to the negative 3 t is 2 pi. We're getting cramped over here. Okay. So we add these two together and we will get 0.0051 t equals 2 pi. So t equals 2 pi divided by that number. And we get 1, 2, 3, 7 seconds. Okay, so we get about 1,232 seconds. And there you go. Next problem is number 14. Maybe I should write the numbers. 14. Alrighty. A space station consists of two donut-shaped living chambers, and there's a nice little picture here. Maybe I should draw it. Alrighty, there's my rough estimation of the space station. Okay, so there's two donut-shaped living chambers, A and B. So the inner one is A. That's this little guy. And then the outer one is B. as the station rotates, an astronaut in chamber A, so, wait, no, we're not doing omega, is moved 2.4 times 10 to the second meters along a circular arc. So that's their displacement. I'm going to say S. So S equals 2.4 times 10 to the second meters, and this is chamber A. How far along the circular arc is an astronaut in chamber B moved during the same time? So we want to find this. And I forgot to draw in the radii. So this radius right here, I'm going to arrow down, that is 3.2 times 10 to the second meters. And this radius right here is 1.1 times 10 to the third meters. So that's radius B, and this is radius A. Now all we have to do is do our handy dandy formula theta equals S over R, because we know S, that's 2.4 times 10 to the second, and then we know R, and this is theta A, but it's going to be theta for both of them, so we don't need to distinguish that. So R is 3.2 times 10 to the second meters. And when we work that out, we're going to get 0.75. And that is in radians. So if theta equals 0.75, equals S over R B as well. Which equals, we don't know SB, but we do know RB, which is 1.1 times 10 to the third. So then we multiply 0.75 times 1.1 times 10 to the third to get SB, which equals, let me find it, 825 meters. There you go. Alrighty, number 19 has another drawing. So I'm going to pause this and draw it, and then I'll come right back. Okay, sorry, this is a terrible drawing, but it works. Let's just pretend that all of the gaps and the blades of this windmill are the same, which they aren't, but let's pretend. So the drawing shows a golf ball right there, passing through a windmill at a miniature golf course. The windmill has 8 blades and rotates at an angular speed of omega equals 1.25 radians per second. The opening between successive blades is equal to the width of the blade. Okay, a golf ball, which has a diameter of 4.5 times 10 to the negative 2 meters, has just reached the edge of one of the rotating blades. Ignoring the thickness of the blades, find the minimum linear speed with which the ball moves along the ground, such the ball will not be hit by the next blade. So this looks like a complicated problem, but we're just going to break it down into parts. The first thing is we know that a full revolution around the circle is going to be equal to 2 pi, and there are 8 blades, and there are also 8 gaps between the blades. So we want to divide that 2 pi by 16 to get the angular displacement of one of the blades, or one of the gaps. And 2 pi divided by 16 is equal to 0.39. Okay. And that's radians. Now we want to know the time that it takes for one blade to travel that displacement right there, 0.39 radians. And since we know that the angular velocity equals delta theta over delta time, we can rearrange that formula to have it say t equals theta divided by omega. So we're going to take theta, which is 0.39 radians, and we're going to divide it by the angular velocity of the windmill, which is 1.25 radians per second, and that will give us t, which is 0.314 seconds. Okay, so we have that. Now we're dealing with the velocity of the golf ball. So v equals the change in distance over time, change in time. We know that time equals 0.314, and we want it to travel past the windmill, so just the diameter of the ball. So that's 4.5 times 10 to the negative second, and that will give us our velocity, which comes out to be 0.143 meters per second. Guess what, kiddos? I think we're halfway there. Next one is number 20. Okay, a figure skater spinning with an angular velocity omega equals 15 radians per second. She then comes to a stop, so this is our final. Comes to a stop over a brief period of time, so we don't know time. During this time, her angular displacement, so angular displacement theta equals 5.1 radians. So we need to determine A, her average angular acceleration, and B, the time during which she comes to rest. So these variables look familiar. You can think of this as just velocity initial, velocity final. This is just displacement. And we want to find A and T. So what formula do we know that we can plug these variables into? So there is VF squared equals VI squared plus 280. So when we plug it in, 0 squared, which is just 0, equals 15 radians per second squared plus 2, we don't know acceleration, and then distance or displacement, 5.1 radians. So 15 squared is 225 plus 2 times 5.1 is 10.2. Okay, I'm just going to write fish because that's what it is. Or alpha, doesn't matter. So then we just move this over. And divide by 10.2, and acceleration comes out to negative 22.059 radians per second squared.
I'm going to eat lunch. I've got pizza rolls.
Now, all we have to do is find time. So we can pull out VF equals VI plus AT. VF is 0. VI was 15 radians per second plus negative 22.059 radians per second squared times time, which we don't know. Negative 15 equals this. Divide. And t equals 0.68 seconds. Okay, now we do 31. At the local swimming hole, a favorite trick is to run horizontally off a cliff that is 8.3 meters above the water. Which equals 8.3 meters. One diver runs off the edge of a cliff, tucks into a ball, and rotates on the way down with an average angular speed omega equals 1.6 revolutions per second. Ignore air resistance and determine the number of revolutions she makes while on the way down. So this is really easy. So first, we just use this formula, x equals vi t plus 1/2 at squared. We know x, that's 8.3. vi, we're talking about the y component because although she has an x component to her velocity, we want to know the time that it takes for her to fall into the water. So we're only interested in the y component of her velocity. So the y component, as she runs off, is going to start at 0. So initial velocity is 0, so that's irrelevant. Plus 1/2 acceleration will be acceleration due to gravity, t squared, like this. Okay. So 8.3 equals 1/2 times 10.81 t squared. And I shouldn't have put a negative here unless I put a negative over here, but we're just going to assume that down is the positive direction for now. So 8.3 equals 0.5 times 1.81 is 4.905 t squared. 8.3 divided by 4.905 equals t squared. So we take the square root of that. And we end up with t equals 1.3 seconds. And from here, since we know that the angular velocity equals the change in displacement over change in time, so omega equals 1.6. We don't know theta, and t equals 1.3. So we multiply those together, 0.6 times 1.3, and theta equals 2.08 revolutions. It's important to note that theta, we're not dealing with radians here, we're dealing with revolutions per second, so your answer is not going to be in radians, it's just revolutions. You could multiply that by 2 pi to get radians, but that doesn't matter. Okay, we've made it to number 40. The Earth has a radius of 6.38 times 10 to the 6th power meters. And it turns on its axis once every 23.9 hours. So 3.9 hours. What is the tangential speed in meters per second of a person living in Ecuador, a country that lies on the equator? And then at what latitude? Okay, I have to draw a picture for this. Give me a sec. Alright, so part B wants us to know at what latitude, which is at the angle theta in the drawing, is a tangential speed 1/3 of that of a person living in Ecuador, which Ecuador is along the equator. So we want to find speed where it's 1/3 of vt. So first we have to find vt. So first things first, we know that omega equals theta over time. And so we know that theta is going to be 2 pi because it's making a full revolution, and the time will be 23.9 hours times 60 minutes times 60 seconds, so we can just say 60 squared. So the angular velocity will come out to be 7.3 times 10 to the negative 5th radians per second. And then we know that tangential velocity, vt, equals r times w, or r times omega. Damn. So we know omega is 7.3 times 10 to the 5th, and then times r, which in this case is 6.38 times 10 to the 6th. And when we multiply all of that together, we're going to get 465.9, and this is in meters per second. So we've got the first thing, we've got the tangential velocity for someone in Ecuador, so located along the equator. Now the problem with this problem is that the Earth actually bulges out at the equator, so this doesn't hold true in real life. But for this problem, we're just going to pretend like the radius of the Earth is the same throughout the entire Earth, that the Earth is a perfect sphere. So the next thing we want to do is we want to find the measure of this angle right here, theta. And to do that, we have to find 1/3 of this velocity right here first. So 465.9 divided by 3, that comes out to 155.3 meters per second. Okay, so we know that the tangential velocity, et, equals rw, and since we know the tangential velocity, it's 155.3, so 155.3 equals r. And when we think about this r, it is not the radius of the Earth. Let me get a new color. It is actually going to be this new radius right here, which will be a little bit shorter than this radius right here. So we are focused on this radius, this new radius right here. So, I don't know, I should denote new radius, Rn for new, times omega, and omega is equal to theta over t, and okay, this is getting really confusing, I'm sorry. So this theta is not the theta that we're looking for, the angle measure. This theta is the angular displacement. So just know that. I'm going to scroll down a bit. So 155.3 equals this new radius, which we don't know yet, times the angular displacement. We're still going to be traveling one full rotation, so it's going to be 2 pi, and time is still 23.9 times 60 squared, because it's a full day. And when we solve for Rn, we will get 2,126,666.67, and that is in meters. So that's our new radius. So let me draw a picture. So looking at the Earth, so we have, this is our new radius. And then here's the axis of rotation. And then here's our actual radius of the Earth at the equator. And we're trying to find theta. Not to be confused with angular displacement, this is an angle measure. So what can we do here? Well, this right here is still the radius of the Earth. So we can draw this triangle. We know this side, Rn, we know this side, that's the radius of the Earth. And let's find this angle. I'm going to call it phi to avoid confusion. Okay. So now what we want to do, we want to find phi, which is complementary to theta, the angle measure that we're trying to find. So we can use trig to find the measure of phi, because we know that sine of phi equals Rn over R. So Rn equals R times sine phi. Wait. Do I really want to do that? No, I don't. Okay. Ignore that. I'm silly. Okay, so the inverse sine of Rn over R is going to equal phi. So inverse sine of 2,126,666.67 divided by 6.38 times 10 to the 6th power, 10 to the 6th power, equals 19.47 degrees. So that's what phi equals. So from here, to get theta, phi plus theta equals 90, right? So, solving for that, this is easy, I don't know why I'm writing it out. Theta equals 70.53 degrees. And that's the answer we should get. There's probably a shorter way to do this, but this is the way that works for me. So, alrighty, we're on problem 44. We have 44, 50, no, 44, 51, and 55, and then we're done. So close. Okay. One type of slingshot can be made from a length of rope and a rubber pocket for holding the stone. The stone can be thrown by whirling it rapidly in a horizontal circle and releasing it at the right moment. Such a slingshot is used to throw a stone from the edge of a cliff, the point of release being 20 meters above the base of the cliff. So we have a height of 20 meters. That's important. The stone lands on the ground below the cliff at a point X. So the horizontal distance traveled is X. The horizontal distance of point X from the base of the cliff, directly beneath the point of release, is 30 times the radius of the circle of which the stone is rolled. So that equals 30 R. Determine the angular speed, so we want to find omega of the stone at the moment of release. Okay, so first off, we want to find the amount of time that this stone is in the air. And since they gave us the height, we can do that. So we use the formula x equals I'm just gonna ignore initial velocity because we're focusing on the y component. So it's the initial velocity is 0, it doesn't matter. So 1/2 at squared. So x in this case is 20. Then 1/2 gravity, so 9.81 times t squared. I'm not going to show the work for this, but t comes out to be 2.019 seconds. So now we know time. So for this problem, we want to find an angular speed, but our displacement is not angular. So we have to work with v equals r omega, and that's equal to r times theta over t. And I'm wanting to get rid of that theta. And since we know that theta equals s over r, if we take this chunk, so theta equals s over r, and then divided by t, and then what else do we have? Times r, times r, times r. We get rid of these r's, so it comes out to be s over t. And what's s? Since we're dealing with a full revolution, assumedly, yes, it's going to be 2 pi. So all of this is just 2 pi over t. I don't want you to get messed up between this t right here and this t right here. This is talking about the time that it takes for a revolution, and this is the time it takes to, upon release, to travel and hit the ground. So just don't get those confused. Now if you took this velocity, this tangential velocity right here, and you multiply it by time, you're going to get displacement. So we can take 2 pi divided by t times the time it travels, which is 2.019 seconds, and you're going to get the displacement. In this case, that's x, which is equal to 30r. And going back to all of this lovely stuff right here, I'm going to start over here and do that same thing. Okay, so we know that Rw, or r omega, equals 2 pi over t, right? So from there, I want to solve it for r, because I want to get this equation down here to one variable, so I can solve it. So r equals 2 pi over omega times t. And then when I plug that in, sorry, I need to see that, 2 pi over t times 2.019 equals 30 times r is now 2 pi over omega t. And now we can solve this for angular velocity, because if you notice over here we have 2 pi over t, and we also have 2 pi over t over here. So now we're just left with 1 over omega. So it's 2.019 equals 30 over omega. And so omega is going to equal 30 divided by 2.019, which is equal to 14.8, I'll call that 6. And that is in radians per second. And that's your answer. 2 to go. Okay, next one is number 51. The sun has a mass of 1.99 times 10 to the 30 kilograms. That's big. And is moving in a circular orbit around the center of our galaxy, the Milky Way. The radius of the orbit is 2.3 times 10 to the 4 light years, which is equal to, 1 light year is equal to 9.5 times 10 to the 15th meters. Okay, so it's that many light years, and the angular speed of the sun is 1.1 times 10 to the negative 15th radians per second. Okay, so this is 2 parts. A, determine the tangential speed of the sun, and B, what's the magnitude of the net force that acts on the sun to keep it moving around the center of the Milky Way? So that's going to be force centripetal, because it's moving in a circle. So we're going to focus on tangential velocity first. So Vt, as we've done again and again, is equal to r times omega. And we are given both r and omega. So r is this many light years, except we want this to be in meters because, we just do. So we need to take 2.3 times 10 to the 4th light years, and then since 1 light year equals 9.5 times 10 to the 15th meters, we need to multiply those two together. I'm just writing this out of order, but it's the same thing. Okay, so when we do that, we end up with a really big number, 2.185 times 10 to the 20th. That's really big. Okay, so plug that in. Times omega, and omega is 1.1 times 10 to the negative 15th. And all of that, when you multiply it out, comes out to be 240,350, so 240,350 meters per second. So that's our answer to part A. And now we want to look at the force that's acting on the sun to keep it in orbit. So if we remember back to, I think, chapter 5, when we talked about centripetal velocity acceleration, we want to look at acceleration, because if you remember, F equals, that's not an equal sign, equals ma. So we want to look at centripetal acceleration, which is v squared over r. I am pretty sure that's right. So to find the force, we have to take mass times v squared over r. And look at that, we have all of those variables already, except for f, because that's what we're trying to find. Okay, so mass, I just looked away from it, silly me, equals 1.99 times 10 to the 30th. And then we want to multiply that by velocity squared, which is 240,350. Okay, all of that squared divided by the radius, which is this number right here, 2.185 times 10 to the 20th. Okay, so I'm going to get my calculator and multiply that out. And for our answer, we'll end up with 5.26 times 10 to the 20th newtons. That's our force. Alrighty. And we're finally to number 55. Okay. A car is traveling with a speed of 20 meters per second. 20 meters per second along a straight horizontal road. The wheels have a radius of 0.3 meters. If the car speeds up with a linear acceleration, so this is normal acceleration, of 1.5 meters per second squared for t equals 8 seconds. Find the angular displacement of each wheel during this period. So we're trying to find that. Now we know that theta equals s over r. Trying to find theta. Do we know s? Do we know the linear displacement? No, but I think we can find it. So we know that x, which is our linear displacement, equals velocity initial times t plus 1/2 at squared. So I'm just going to call x s to make this easier. What's our velocity initial? 20 meters per second times time, 8 seconds, plus 1/2. Our acceleration is 1.5 meters per second squared times t squared, which is 8 squared. Alrighty, I'm going to put that in my calculator. And s comes out to equal 208 meters. So we have theta equals s, so 208 over, what's r? 0.3 meters. So all we have to do is divide those out, and we come up with 693.3 repeating. And that's radians. And that's it. We're done.